Welcome to Civ Academia channel. We will solve stiffness matrix method and apply the method to a continuous beam having degree of freedom is equal to 1. Then finally we will draw the shear force diagram and bending moment diagram for this indeterminate beam. Now stiffness matrix method basically is solved by this formula where K is nothing but the stiffness. So what is stiffness? Stiffness is nothing but K is represented by K is equal to the low force due to unit displacement. So when the displacement is equal to 1, the stiffness is nothing but the force that is getting developed when you give a unit displacement, or you can give unit rotation also. So this rotation is corresponding to the moment. Okay. So the stiffness is basically defined as the force or moment which is due to unit deformation. Now this delta is the unknown deflection or rotation. So here you can see that the stiffness matrix is multiplied by the delta matrix. Now here this delta is the unknown, and we will develop the stiffness matrix K. So this K is the stiffness matrix and delta is the unknown deflection or rotation. And what is P? P is nothing but the external forces in the coordinates 1, 2 and 3. So suppose you have coordinates here like this. Now if this is the beam, here there are 2 degrees of freedom or degree of indeterminacy, which is said to be 1 here and this is 2. This is coordinate 1, this is coordinate 2. So you can see that coordinate 1, 2, 3 and so on. So it depends upon the rank of the matrix depends upon the stiffness matrix depends upon the number of coordinates that you are taking. And the size of the matrix is also depending upon the number of coordinates. If you take 2 coordinates, the stiffness matrix will be of 2 cross 2 matrix K11 and K12, then here K21 and here you have K22. So this is 2 cross 2 matrix. If the degree of kinematic indeterminacy is 2, here you will get 2 cross 2 matrix. But in our problem, the degree of freedom is only 1. So you will be getting only one element in the stiffness matrix. So this stiffness matrix which we are going to solve is 1 by 1 cross 1 matrix. So here in this continuous beam which I have shown you, there are 2 coordinates, and so the matrix is of size 2 by 2 matrix. And what is P matrix? P matrix is nothing but the external load which is present in the coordinate. For example, here there is no external load at this coordinate 1. Here there is no external load. So this P matrix is generally 0. But if there is some overhanging portion like this, for example, if there is an overhanging portion for this beam and it is acted upon by some load, for example, here there is some load and this distance is A. So in such a case, you can see that this P multiplied by A can be applied to the roller support in the form of moment PA. So in such case, you will find out that the P matrix is nothing but the P matrix, you will get the value of P into A. Now what is PL matrix? PL matrix is nothing but if you assume the structure to be restrained and on basis of this restrained assumption, you will be finding the fixed end moments. So that is said to be PL. So PL is the load in the coordinate 1, 2 and 3 due to restrained structure or constrained structure. Okay, that we will see in the upcoming slides. Now this is the beam. Now you watch the beam, that this beam is having 2 spans, which is AB and it is followed by BC. Now this span AB is having moment of inertia I, and the span BC is having moment of inertia twice that of the span AB. And here there is a load which is applied at the center, which is said to be 40 kilonewton in the span AB, and the span BC carries a uniformly distributed load of 20 kilonewton per meter, and the span is 6 meter. Now here what I will do is I will apply a unit rotation here. So if you give a unit rotation, basically what happens is you will have the shape like this. This will be the shape of the deflected. This is the deflected curve. Now here theta equal to 1, and here also theta will be equal to 1. So you have given unit rotation. This is said to be unit rotation. Now at the farther end you can see that theta c is 0, and here also at the span AB the theta A is equal to 0. So this is the basis for the problem by which we are going to solve by stiffness matrix method. Then we will draw SFD and BMD. Now what I told is here you are applying the degree of freedom, that is equal to 1. So here this roller will permit a rotation. So here only rotation is permitted. There is no vertical deformation, or there is no horizontal deformation which is permitted. So the degree of freedom or kinematic indeterminacy is only 1, as I said earlier. Now we will proceed further. Here the first step is to calculate the fixed end moments. As I told you, what we have to do is we have to constrain the span AB. So let us constrain the span AB here like this, and we will estimate what is M of AB, and also we will find out what is M of BA. You understand? So for this span there is a load at the center which is said to be 40 kilonewton. So based upon this 40 kilonewton, you can evaluate that the fixed end moment AB is minus WL times 8, and the length is 4, load is 40, and here we see that the direction of the fixed end moment is anticlockwise, so it is minus 20, and here if you take for M of BA, that is fixed end moment for the span from here to here, from B to A, it will be here, this is B and this is A. So that will be nothing but WL by 8, the same thing, because the loading is symmetric. So you will get 20 kilonewton meter. Then you take this span BC, and the BC is restrained like this. You are restraining the span BC like this, and you are trying to evaluate the fixed end moment due to the UDL which is applied here. So because of that you will get minus WL square by 12 and plus WL square by 12, that is minus 60, and here it is plus 60. Then you can see that here we are applying a unit rotation. So at this location theta equal to 1, at this location theta equal to 1, and here you will get theta C as 0 and theta A is 0, because you can see that these two ends are basically fixed. So if you carefully observe, you will find out that there is no rotation at all at these locations, hence the theta C will be 0 and theta A will be 0. Now I will call this coordinate B as 1. So I will evaluate what is K11. Now you can see that I will explain you here what is the subscript 11 stands for and what is the subscript 21 stands for. For example, here if we apply a rotation here at this location and this location, this is 1 and this is 2. Now here we can see that here it is called K11 and here it is called K21. So if the stiffness at this location, particular location 1 is K11 and the stiffness at the location 2 is K21. Now what is the first subscript and second subscript represent? So this represents the location where you want to find out the stiffness, and this one represents the location where you have given the theta equal to 1. For example, if you take this point, here K21 is there. 2 is the location where you want to find out the stiffness. So location of stiffness, where you want to find out the stiffness. And what is 1? 1 is the location where you have applied the rotation theta equal to 1. So this is the real meaning. So you can find out that the first subscript represents the location where you want to find out the stiffness, and the second subscript represents the location where you are applying unit rotation. So here you can see that it is K11, and here there is no K21 or no K31. No need to worry about, because here only 1 degree of freedom that is available at point B. Yeah, here you can see that the moment at point 1 due to unit rotation at point 1. Now here, as I already explained, 1 stands for the stiffness. So here it is moment at the point 1 due to unit rotation at point 1. So this 1 corresponds to this point 1, that is rotation, and this one corresponds to this moment. Okay, this you have to remember throughout this derivation. Now we have to apply the slope deflection equation for the spans AB and BC. So first let us apply the slope deflection equation for the span AB. So if you do that, 2EI AB by LAB into 2 theta B plus theta A minus 3 delta by LAB. So these concepts are obtained from the slope deflection method that you already know. So I assume that you already know slope deflection equation, and this is 2EIBC by LBC into 2 theta B plus theta C minus 3 delta by LBC. So basically the slope deflection equation goes like this, 2EI by L into 2 theta B plus theta A minus the settlement, that is delta, by L. This is the equation. Okay. For example, if you consider the span like this here, and you have this. So for this span, you can see that this is L AB. This is A. This is B. I will explain only for one span. So this span AB, you have a value IAB. Okay, IAB, and the length is LAB. So here we can write IAB, and here you can write LAB. Okay. Now if you apply from this point, so from this point if you apply, it is 2 theta B plus theta A minus 3 delta by L. If you apply the slope deflection from this point, you will get another equation, 2E IAB by LAB multiplied by, since you are applying the slope deflection equation from point A, here you have to take 2 times the theta A plus theta B minus 3 delta by L. So this is the case. Now it depends upon from which point you start writing the slope deflection equation. So this is the equation for the moment AB. So this final moment you have to add the fixed end moment also, m of AB plus, so you will have fixed end moment plus this expression. So this is for this one. Similarly for the BA, you can write down m of BA plus this these terms for M. For what is MEAB? MEAB is the final moment that you want to solve. Now here you can see that we have 2 spans here, and basically it is applied from the point B. So here you are applying here MBA you will calculate using slope deflection equation, and here you will calculate MBC. Okay, so because of that only you are having two expressions here for the span 2E IAB by LAB. You multiply 2 times of theta B and add 1 time of theta A minus 3 delta by LAB. Then you have 2 EIBC by LBC into 2 theta B plus theta C minus 3 delta by LBC. Here you can see that IAB is I and IBC is 2I. So you have to substitute here 2I, and you have to substitute here I. Then theta B is 1 as you already applied the theta B equal to unity, and theta A and theta C are 0. So these things you substitute in K11, and if you do that, finally don't worry about the calculations, very simple. You have to apply theta B equal to, you have to put theta B equal to 0 and theta A equal theta B equal to 1 and theta A equal to 0 and theta C equal to 0. Also put delta equal to 0, delta equal to 0. Then finally you are getting the stiffness coefficient K11 equal to 7EA by 3. Now, yeah, as I told you, this is the stiffness method that is being used. Then you remember this formula that K multiplied by delta is equal to P minus PL, and delta 1 is theta B. Okay, so this is theta B, and K11 equal to 7EA by 3. P, as I told you, the external loading at these locations. At this location, roller support, for example, let us draw the beam again. So for this beam, at this point, there is no external load or moment. So P is equal to 0. Then PL. So here, if you want to calculate the PL due to restrained structure at this location, you can see that at this location you have plus 20, and here in the span BC you have minus 60. So you have to add all these things, and finally you will get minus 40 kilonewton meter. That is PL. So you know P equal to 0, PL equal to minus 40, del equal to theta B, and K11 is 7EA by 3. Substituting all the values here, you observe keenly, this delta is nothing but theta B, and K is 7EA by 3 as you calculated earlier, and substitute P equal to 0, substitute PL equal to minus 60, then you have plus 40. Then from this equation you are going to obtain the value of theta B equal to 120 by 7EA. Okay, so we have obtained what is theta B, and we know what is theta A, and we know what is theta C. Now you apply the slope deflection equation. So these are the slope deflection equation for all the 4 moments concerned with the span AB and BC. So here you can see that MAB equal to M of AB plus 2 EIAB by LAB into 2 theta A plus theta B minus 3 delta by LAB. Similarly for MBA, MBC, MCB, you are getting all the values. Then finally, as I told you earlier, substitute this theta A equal to 0, theta C equal to 0, del is 0, there is no settlement or sinking of supports, and you substitute theta B equal to 120 by 7EA, which has been obtained by solving using this stiffness matrix method. Then after substitution of all the values, you get here minus 11.42 plus 37.14 minus 37.14 and 71.42. So you can go through this table for explanation. These values will guide you to calculate the final moment. These are final moment value. And bending moment by parts. So for this beam, first we draw the bending moment here. At this location, as you know, it was 11.42. So this bending moment diagram is drawn by parts. First you consider the moments which have been calculated earlier. That is here you have calculated the final moments as, so these are the final moments using the slope deflection equation. 11.42, it was negative. Here at this location negative is upwards, and at this location positive is upwards. So you join them with a straight line. Then here it is 71.42, you join them with a straight line. So this is due to the MAB, MBA, MBC and MCB. What about the loadings? What about the moment due to loadings? That we will calculate in the next slide. So this is the loading. We assume these two beams to be simply supported and calculate the corresponding moment as WL by 4 and WL square by 8. Now the values are 40 and here this value is 90 and this value is 40. Now already you have drawn the moment diagram for final moments using slope deflection method. So overlap these two diagrams to obtain the final bending moment diagram. So you can see that 11.42 here you have 11.42 and here you have 37.14 plus or minus minus and plus, and here you have 71.42. So overlapping these two diagrams due to final moment which was obtained from slope deflection equation, and considering the beam as simply supported beam, we had two spans AB and BC, and because of that we evaluated this 40 and 90 and you overlap them, you get the final diagram. This moment is here it is positive, this is positive and this is positive, this is negative, this is negative and this is negative. Now how to find out the reactions? We have calculated the moments here, we have calculated the moments at these locations, so don't worry about the sign. If the sign is negative, you take it as anti-clockwise. If the sign is positive, you take it as clockwise. Don't and forget about the sign. So you split this beam into the continuous beam into two spans which are simply supported, and apply the loadings and moments. Then you take the span AB separately and take the span BC separately. Here you can see that at the point B, for both the spans you have RB dash and RB double dash. If you add RB dash plus RB double dash, you will get the reaction for the continuous beam, which is nothing but RB. RB equal to RB dash plus RB double dash. So first let me take the span, this span AB. Take moment about point B dash. So this is B dash. Okay. This is B double dash. So take moment about these points and you will find out that RA multiplied by 4 and this moment is clockwise moment. So RA into 4 is also clockwise. So this is clockwise, this is clockwise, this is anti-clockwise, this is anti-clockwise in this span AB. So this is anti-clockwise and this is also causing this anti-clockwise. 40 into 2 is also causing anti-clockwise, then equal to 0. You are taking moment about this point. Okay, this point is taken and you are taking moment about this point and equate it to 0. You end up with RA equal to 13.57 kN. Then after that you calculate that RB dash. RB dash equal to 40 minus RA. So that is equal to 26.43. Then you find out, then you take the span B double dash C, and in this span you take moment about this point and equate it to 0. So RB dash into 6 is clockwise, 71.424 is clockwise, and 2 into 6, this UDL, 2 into 6 multiplied by the centroid. So this is the centroid of the UDL, that is 3 meters. So this is 3 meter. So 2 into 6 into 3, this is anti-clockwise, and this minus 37, this is minus 37 point here. Now you have to put the minus sign. Okay, so minus 37.143, this is anti-clockwise. So you get RB double dash equal to 54.28. What is RC? RC equal to total load. Total load due to UDL multiplied by 54, subtracted by 54.28. So RC equal to total load minus RB double dash equal to 65.72. So you get RC equal to 65.72 and RA equal to 13.57. RB equal to 80.71 kilonewton, which is nothing but RB dash plus RB double dash. Now you have got RA, RB dash, RB double dash and RC. So if you want to draw the shear force diagram, you draw a line like this. Here it is 13 point, so you can put arrows like this, 13.57, and you draw a line here. At this location it is 13.57 minus 40. So you will get here minus 26.4, which will go up to this location, and here it will be 80 minus 26.42, and at this location you have 65.72. then you join this. So this is 80 minus 26.42, which is nothing but 50. So this is 54.28. So it will be shown in the next figure. So this is 13.57 up to this location, and here 40 minus 13.57 minus 40, because 40 is downwards, that is, this is minus 26.429. This is minus 26.429 plus 80. If you add at this location, you have 80, because the total is 80. So if you add this, you will get this 54.28, which is positive. And at this point you have negative, because it is right side, on the right hand side it is upwards, which is negative. Then you join this with the straight line. Now I leave it to you. You can calculate the location at which the shear force is 0. What is the x value? How will you find out that? That you will find out from there is RC minus 20x equal to 0. You solve and find out what is the x at which the shear force is 0. Okay. So thanks a lot for watching. If you have any doubts still left out, that you can mention in the comment section. Subscribe the channel. Thank you.